All right, guys, it is 10 o'clock and I would love to get started. We have a lot of ground to cover today. Hope that your week is starting off well. I don't know if you realize this, we're almost halfway through the semester. I think next week we'll be halfway there. So it goes by fast. I feel like we just started, but here we are. As far as this week goes, homework number 10 is the main thing on our radar, but I split it into two assignments because we've already covered 4.4, but then the other problems are from 4.5 and 4.6, which we haven't covered yet. So the 4.4 part is due tonight at the end of the night. I do have a lot of office hours, as always, later in the day, so you can stop by and talk to me and ask for help with anything that we don't have time to get through during class today. I will, of course, be glad to do my best to give you some hints and pointers on all of that. And then, so then that second half of homework number 10 will be due on Friday night. And I'll take questions on that assignment on Thursday in class as well. So there'll be chances to ask me questions there as well. So guys, we talked last week. I'm just going to give you the quick reminder about where we left off. Two main things that we want to be able to do with spanning sets. There's two main questions about spanning sets. Remember, guys, a spanning set is like a building blocks collection of a vector space. These are specific vectors that can span the whole vector space if I form linear combinations. Okay, so what are the two main things we want to be able to do with spanning sets? The first one is we want to be able to find a spanning set for any vector space. And we practiced several examples of this last week. It's basically a three-step process. And I called it A, B, and C here. The first thing you need to do is write down, what does a general vector in V look like, right? So put it in terms of letters. Whatever variables you have, you can use those variables to express the general form of what any random vector in V would look like. Okay, so there's going to be some variables that you have to introduce there. Okay, that's the first step. Then the next thing is we have to bust out the variables from the first step. So in the first step, you will have variables that you have included in your general form. You then just need to bust them out, as I like to say, or in other words, factor them out. And once you've done that, the only thing left to do in part C is part C is a quick, easy wrap up. You just make a list of the specific vectors that are left behind. Okay? So we did 4 or 5 examples of this on Thursday last week, so I won't do a warm-up on this right now, but we might have some homework questions on it, so I will come back to that point. But instead, I'll move on. Unless is there any question about that? This is just totally review from last Thursday. If I want to find a spanning set for any vector space, I have to follow these 3 steps. Yes?
Just fairly quickly. When it's consistent, that means that the pivot is within the not where the
it's on. Okay, so first of all, that's dealing with question 2,
yeah,
which I haven't talked about yet.
Okay.
But consistent just means that the pivots do not go into the far right.
Okay.
Yeah, exactly. And so that's the second question, guys, is to decide yes or no. If somebody gives us a set of vectors, we can ask, would they be a spanning set for V? Would they form a spanning set for V? And we only did one example of that in class last Thursday. What we noticed in that example is that we can answer this question. Again, the blue writing is how you do it. You basically lay your vectors into the columns of a matrix. And you augment that matrix with, you notice I put this number symbol notation here. That's supposed to represent, like, again, a general vector in V. So you're asking, is it possible for these vectors to span all vectors in V? Is it a spanning set for V? So an arbitrary vector in V would normally have letters with it, just like in step A of the first question. There would be variables or letters. And when I first went over this on Thursday, I was putting letters into the far right column here. But what we noticed is that as we do EROs to try to decide if this is consistent or not, those letters just get changed into other letters that arise from sort of doing those EROs. It's just an alphabet soup of whatever those letters were that you originally wrote down. And you don't need to keep track of that. You generally don't need to keep track of that. So what you get then is just number symbols. And if this system is consistent, that just means it has a solution. There's no pivot in the far right column, right? Then the answer is yes, you have a spanning set. But if it's inconsistent just means the pivot went into the far right column, then that's bad, right? That means there's 0 solutions to your system. That means it's not possible to span your vector space with those vectors. So you're going to see pretty much for the entire day today, in that far right column, I'm going to just be throwing those number symbols. There's only one exception to that, which is the homework problem number 40 that's over on the sideboard. And I want to, well, I'll come back, maybe I'll come back to number 40 in just a minute, okay? That's a slightly different question, but for the most part, question number 2 is just deciding yes or no, do your vectors form a spanning set for V? Okay, so let's do these 2 warm-up problems first, and then I'll do number 40 from the homework. This question and the warm-up is focused on number 2, right? Decide yes or no, is the set that they gave you a spanning set for V? So let me just show you just how quick and easy this can be, right? So for number 1, I'm going to take the vector space of R2, and I've come up with 4 vectors here, right? And so what I would do to solve this problem, following the rubric in blue here, I would lay my vectors vertically into the columns. Now, by the way, that sometimes throws people off. It's like, I thought we usually fill out a matrix row by row by row, and that is true. When you're solving a system of equations, you normally fill out the matrix row by row, but here I'm going to fill out the matrix in columns. V1 goes here, V2 goes here, V3 goes here, and V4 goes here as columns, right? We could label these, right? These vectors, this is V1, this is V2, this is V3, and this is V4, just to have them labeled. And we lay those out vertically. And I'm going to augment this matrix with number symbols. Remember, this is really an X and a Y, or it's an A and a B, whatever letters you've chosen, whatever variables you might have used to represent that general form, that's really what goes here. But again, my point from last Thursday was it doesn't matter what those actual letters are. When you do these EROs, they just stay as letters. By the way, I also had a video for you guys to watch for tonight, and it has this kind of problem on it as well. So we're kind of reviewing something that is already in the video notes. Yes.
In the true or false homework, there's a question that asks about whether it's the B must be uniquely expressible as a linear combination. Is there any correlation to this?
Not really, but I can answer that question right now. Does a vector have to be uniquely expressible as a linear combination? That is false, because unique is the word that is important there. Unique means only one way to do it. And I would answer that that is no. For example, if I take the vector, in this example, if I take the vector 10, 9, I can write that as the third vector added to the fourth vector. They just add this third and fourth vector. Or I could also instead write it as 10 times the first vector plus 9 times the second vector. So I'm just now, right now, guys, if you want to know, I'm doing true, false, item, I think it's D from today, from the homework assignment. So is it true that, and this one's not true, is it true that every vector in your vector space can only be written one way in terms of your spanning set? And the answer is no, and this is an example of that.
There would be a basis, right?
Well, I haven't gotten to that yet. Let's hold off on that. Yeah, if it was a basis, as we'll discuss later today, then it would be unique. But for a spanning set, the answer is no. So let me come back to this blue solution I'm doing. I lay my vectors into the columns of this matrix, and then I need to get it into row echelon form. But guys, I picked a very nice example here. It's already in row echelon form. I'll circle my pivots, as I always should do. And can you tell me, is this consistent or not consistent? It is definitely consistent. And so there's no pivot in the far right column. And so this is a yes. Decide if S is a spanning set for V. The answer is yes. It's just that easy, okay? Let's go on to the second warm-up. On the second warm-up example, I'm working in a different universe now, right? I'm going to work with 2x2 matrices, and here's the 2x2 matrices. Again, we could label these as B1, B2, and B3. And I'm going to lay these, I'm going to make this matrix again. Now, here's the weird part, guys. Each one of these individual matrices becomes a single column of the matrix that I'm doing in this setup for the solution here. So I take this entire matrix B1 and throw it into column 1. And you notice what I did, I grabbed the 1 and then the 2 and then the 2 and then the 2. And I just made a column out of that. Okay. The second vector, I'm going to do the same thing, 1 and 3 and 0 and 1. And the third one, 0 and 1 and 1 and 0. Now, people will usually ask me, does it matter what order I put those 4 entries into this column? The answer is no. You can do these 4 numbers into this column however you want. The important rule is, the caveat on that is that you must do them all the same. So if I go upper left, then upper right, then lower left, then lower right on the first column, then I have to do that on the second matrix as well. Upper left, upper right, lower left, lower right. Upper left, upper right, lower left, lower right. As long as I'm consistent with how I plucked out those numbers from the matrix, is totally good. Okay, and then I need to augment this with those number symbols again. And again, they really are the variables that would have been representing a general 2x2 matrix, right? My universe here is M2 of R. So this is really like an A, B, C, D, or if you want X, Y, Z, W, whatever the letters are, but I don't have to keep track of what those letters are. And now, guys, I'm just going to do EROs. I'm just going to do EROs. I've got my first row already has a pivot in the top row, so I'll leave that the way it is. And now I'm going to do 3 EROs at once here, guys. I'm going to get zeros below that pivot in all of the lower rows. And so I'm going to need to take, what is it, A of 1, 2 of -2, right? So -2 times the first row added to the second row gives me a 0 and a 1 and a 1. And guys, we don't even have to turn on our brain over here on the far right. It's just some other number symbol again. We just keep writing those number symbols down. And now I'm actually going to have a pivot there as well. Let's do A1, 3 of -2. So that gives me this 0. It gives me a -2. It gives me a 1, and it gives me a number symbol again. Okay, and then let's do A1, 4 of -2. That gives me a 0 in the bottom left corner, and then a -1, and then a 0, and then a number symbol. Just like that. Okay, and my three vectors are just lined up into those three columns as I've kind of shown there. And now I'm gonna just do one more step here. I'll leave the first row the same and the second row the same. I'm just copying number symbols into the far right column. By now, the far right column is really a messy, mishmash of A, B, C, and D, for example, right? But I don't have to keep track of that. So I just put number symbols there. Let's take A2, 3 of 2. It'll give me a 0 and a 0 and a 3 and a number symbol, I believe. And then, is that right? Yeah. And then in the bottom row, so that's going to be a pivot there as well. And then in the bottom row, I'm just going to do A2, 4 of 1. So it would be 0 and 0 and 1 and number symbol. And then the last thing I'll do is just, I'm going to leave the first three rows the same. I don't know if you guys have noticed this. I've gotten a little sloppier with EROs now. I'm not even going to change that 3 into a 1. We could, but what's important is the position of that pivot. But using a -1/3, I can zero out the one that's below it. And here is where we finally get the answer to this problem. In this last matrix, guys, you see that the pivot has drifted onto that number symbol. The number symbol is always a pivot if it's the first non-zero entry in that row. And that tells me, is this a spanning set for M2 of R? It is not. It is not, because it's inconsistent. Inconsistent means no here, right? Oscar.
You spoke about determinants on the video.
Yes.
You
can't use that here.
Okay.
This is not a square matrix. I can't even use that here. So we'll get to some examples where we could use determinants, but right now it's a no can do on this problem.
Wait, so when you did the euro to take out that 1 and make it a 0, that affected the right column?
Well, it changed what's over here, but it's still just being represented as a hashtag number symbol. So it would be some mishmash of A, B, C, and D, right? That is in this far right column.
But how come when you did that earlier, why wasn't any of those affected?
These are all affected. So I don't know quite what you mean. This is like A, B, C, and D. When you do these EROs, these things change.
Yeah.
And here they change here, then they change again here, and then they change again here. But the point is, they just still involve A, B, C, and D. They are not 0, is the point. Yeah. Yeah, so the only exception to putting these number symbols in the far right column would be if you had a specific polynomial or a specific vector that you were trying to see if you could span it using your set. And that's exactly what problem 40 is. So maybe I'll take just a minute and show you problem 40 from tonight's homework. This is from 4.4, number 40. What it says is they give you P1 of X. So this is a polynomial example. P1 of X is X minus 4. And then P2 of X is X squared minus X plus 3. And then they give you P of X. The question is P of X, which is equal to 2x squared minus X plus 2, is that an element of the span of P1 and P2? This is what problem 40 is from tonight's homework. So they're going to ask you whether this polynomial is in the span of these two. This is like V1 and V2. So the way you would solve this problem is almost the same thing that's in blue right here. You're going to lay these polynomials into, so for the solution for this problem, you're going to lay these polynomials into the columns. Now, notice that we need an x squared position, an x position, and a constant position. The x squared position is actually not showing up in the first polynomial, but there is one x and there's -4 constant. So that's just P1 being smeared out into a column. In the video that you watched over the weekend, I sort of showed how the polynomials go into these matrices. You don't see the x or the x squared here at all. You just see the coefficients, just the numbers that are in front of the different terms of that polynomial. The second polynomial has a 1 on the x squared coefficient, a -1 on the x coefficient, and a 3 on the constant term. And here's where normally I would put number symbol, number symbol, number symbol here to see if these two polynomials span P2 of R. The whole universe of P2 of R, I would put number symbols there. But why did I say this is the only exception to the number symbol thing? Is because they gave you a specific P of X that they wanted you to check out. So we're going to put the coefficients of that polynomial right here as such. And the idea will be to try to figure out whether this is consistent or not. So again, I'll probably move the second row to the top just so that it has a pivot in the upper left corner. I'll move the first row to the second row. Move the first row to the second row. And then let's take 4 times the first row and add it to, 4 times this middle row and add it to the bottom row so we can get a 0 here. And we should get 0 and -1 and -2. As I do that ERO, and then we can circle this pivot, and I'm going to do one more step here. You can actually see that the bottom 2 rows are pretty much just multiples of each other. So if I add the second row to the third row, what happens is I get 0, 0, and 0, which means, is there a pivot in the far right column? There's not. And so is this consistent? It is. And therefore the answer to this question is yes. It is actually a yes. Right. So that's pretty nice. It just means, what that means, guys, is that this specific polynomial could be written in terms of these two. That's what it's telling us. I bet we could even figure out how to do it, right? If I want to write this polynomial in terms of these two, it looks to me like the P of X, what would it be? It would be 2 times P2. So if I double this one, right, and then add P1 to it. This is just me kind of guessing at it in my head. But if I take double this one and then I add this one to it, I get this one. You can check. So, well, that's just another way of saying that P2 is, so yes, it is a linear combination of the other 2 vectors, which means it is in this span. So it's a thumbs up. Does that make sense? That's number 40.
So, Professor, technically, like, if we go straight into that without having to do the matrix?
If you notice this off the top of your head, you could just write this equation down and say yes immediately. However,
because they're in the same format, right?
Well, this is what it means for P of X to be in the span of P1 and P2, right? The problem with it is you got to figure this out in your. I mean, I did it in my head because I've done this problem for 20 years. Right, but if you've never seen this before, you might be scratching your head. I don't know, can I write this polynomial in terms of these two? It might not be obvious to you. So if it's not obvious to you, the foolproof way to make sure you get the answer right is to set up the matrix. And that is what you should do. By the way, let me just ask you a follow-up here. This is all you need for the homework problem, but just as a follow-up, would P1 and P2 be a spanning set for the entire P2 of R?
No.
I don't think so. Why not?
Because, I mean, if you look at P1 compared to P2, P1 only has a degree of 1, P2 has a degree of 2.
Mm-hmm. That wouldn't necessarily convince me that it couldn't be a spanning set for P2 of R, but what would convince me, guys, What would convince me is that if I change this far right column, okay, don't change your notes, okay, because I'm just doing a little extra add-on. If I change this to what I would have to have for a general form of a polynomial in P2 of R, I would be using these number symbols. And if I go across the way and change these to number symbols, now you can see that you would have a pivot in the far right column now. Okay. So all we're saying at, guys, is that P1 and P2, they do not span the entire universe of P2 of R, but they did span at least P of X. They span some of the polynomials in P2 of R. Can I say something kind of silly and idiotic sounding? A set of vectors will always span whatever they span. Like these vectors have a span, right? You can take all possible linear combinations of these vectors, and of course these two vectors will span that. Now, whether it's the entire universe of whatever you're living in is not clear, but a set of vectors will always span whatever they span, which is something. They have to span something. Of course, what it is a subspace of P2 of R, right? Anytime you take the span of anything, you always get a subspace. And yeah, P1 and P2 would be a spanning set for the subspace that they actually created, right? So that's kind of a whoop-de-doo kind of a conclusion. It's like, yeah, of course the two vectors are going to span whatever they span. The more interesting question is, do they actually span your whole universe? And the answer here would have been no. But thankfully, we were only trying to span this one guy, and so the answer was a yes. Does that make sense? Yeah, Anthony?
Doesn't that answer A, true or false?
A span of vectors forms a subspace of V. Is that the one you're talking about? You can just say yes, because Dr. Annan has said 100 times that anytime you take the span of anything, you always get a subspace. Yeah, that is very true. That is very true. Okay, guys, I hope that this is making pretty good sense. Now, I would like to ask a question. If my goal was to span my vector space V, if I was really trying to find a spanning set, just back to what the first question was, right? Find a spanning set. Couldn't I just grab 500 vectors out of the sky? If I really wanted to span P2 of R, couldn't I have just grabbed 500 polynomials, which would make this matrix have 500 columns? If this matrix had 500 columns, it's not very likely that that pivot is going to scoop 500 columns to the right. Chances are you're not going to have a pivot going into that far right column. Right? Same thing here with this R2 example. I had these 4 vectors. The more vectors that I would have had, the wider this matrix would have become. It would have been even less likely that that pivot would scoot into the far right column. Okay? But now I'm going to change the rules on you. I'm going to change the rules on you. Every time you put a vector into your spanning set, it costs you $1,000. It costs you $1,000. So right here, I spanned R2. The answer was yes, but it cost me $4,000 to do it because I had to use 4 vectors to make that happen. You with me? Okay. And if you realized that that was going to cost you $4,000, you might have said to yourself, you know what? I didn't need to buy this one. Think about it. If I didn't have 8-6, then when I was setting up this matrix a few minutes ago, I just wouldn't have had this column there. But would my pivot have gone to the far right column? No, I still would have had a spanning set, and now it's only costing me $3,000 instead of $4,000. And actually, what about the vector 2, 3? Don't need it. I don't need it. If I get rid of it, if I go back for a refund, I don't want to spend $1,000 on that vector. That just means I would lose this column. But what's still showing in blue here, guys, the matrix that I still have is still going to have pivots that stay out of that last column. And that's a good thing. The answer would still be yes. So I would like to address the question of not just finding a spanning set for V, but finding a cheap spanning set for V. I want to find the cheapest one that I can, and this is the topic of linear independence. And I'm going to add this title here for this next section. This is 4.5 that we're going to start right now. Linear independence. Okay, so let's get the heading here for this next little section. This is called linear dependence / linear independence. Kind of a long title here, linear dependence and linear independence. I don't like to keep writing these long words out, so I'm going to very quickly start referring to these as LD and LI, linear dependence and linear independence. And I haven't explained what these words mean yet, but I'm just going to I want to get you in the mindset of what's coming, that linear dependence is, you should think of that as a bad thing. You don't want vectors that are linearly dependent. And linear independence is actually what you would really, really like to have. That's a good thing. So any set of vectors in any universe whatsoever is either going to be Li or LD. And if it's LD, that's bad. If it's Li, that's good. Basically, LD is going to mean too expensive. We spent too much money on it. Li is going to mean we did the cheapest that we could. We got a cheap set of vectors in front of us. So let me put down the definition of what these words mean officially for us in our notes here, and then we'll go from there. So a set, and I'll make this into a set of V1, V2, and ... up to Vn, is LD, linearly dependent. Remember, that's a bad thing. These vectors are LD if at least one of them, if at least one of the vectors can be expressed, at least one of the vectors can be expressed as a linear combination, of some or all of the others. So if you have a set of vectors, and if you can write one of the vectors in terms of the others, that's LD. That's a bad thing. Otherwise, the set is Li. So it's one way or the other. Your vectors are either going to be LD or they're going to be Li. You guys with me so far? Let me give you an example. Let's look at number 1 above. This first example from above. And let's, okay, I crossed off these vectors, which I shouldn't have done. Well, I was just trying to show you something. Let's put this back the way it was. I cross off these vectors, and I don't want them crossed off anymore. So let's go back. We've got 2, 3, and we've got 8, 6 here. And this was V3, and this one was V4, just to get it looking the way it was before. Okay? And I can very easily give you an example to show this, how this definition works. if you look at the vector 8,6, which is the V4, well, I can write that in terms of V1 and V2. Namely, it's 8 times 1, 0 plus 6 times 0, 1. And what I have just written down on the board here, guys, is a bad thing. Because what we're saying is that the fourth vector was just 8 times the first vector plus 6 times the second vector. And this is what we didn't want to see happen. We don't want to see this happen. So just again, check the definition. At least one of the vectors, that's 8, 6, can be expressed as a combination of some or all of the others, in this case, some of the others, V1 and V2. The V3 is not showing up here, but that doesn't matter. This is already an LD set as it is. I just want to explain why this is a bad thing. Would you guys ever go out to the store and buy something that you could already build out of what you have at your house? I wouldn't do that. I would save by my guys. You can already build V4 out of V1 and V2. So why would you spend $1,000 on the vector V4 when you can make that vector for yourself by using V1 and V2? This is why this is expensive, right? This is not a good. It was a spanning set. Okay, I'll give it that. That was a good thing, but it's not a cheap spanning set. This is an expensive spanning set because V4, we paid $1,000 for that vector when we could have just made it from scratch out of what we already have in front of us. Okay, so that's right. And sometimes you're going to see me rewriting this one as an equation equal to 0. So let me just show you that right now. So if I subtract everything to one side, I would get this equation right here. This is called when I see this kind of an equation, this is called a linear dependency. This is a linear dependency, and it is a bad thing if we have that. Yes, Oscar.
Kind of like similar to the other column where you stated that the vectors kind of all go in one place. They're all pointing at the same spot. Would V3 and V4 be the same case where it's just pointing towards the same general direction?
Well, general direction isn't good enough. That's too loosey-goosey. But I mean, none of these vectors are pointing parallel to another vector, right? They're all pointing in a slightly different direction. Like we could graph these vectors. 1, 0 is here, 0, 1 is here, 2, 3 is there, and 8, 6 is there, or something like that, right? So it's 4 different directions for those vectors to point. It's good to think about the geometry of it. I'm going to come back and say a little bit more about that in just a little bit. Okay. Let's do another example. Come back over here for this one. The next example, I think I'll use some polynomials just to give us a different feeling for it. I'm going to give you a set of vectors, and I'm going to ask you, are they Li or are they LD? Okay? Every vector, guys, every vector that you create costs you $1,000. This is the way I want you to think about this one. So here's the example. Is the set of 1 plus x, 1 plus x squared, 1 plus x squared plus x cubed, and x plus x cubed, is that Li or LD? I should have written the conclusion out here. So what I meant to write here, guys, is that this set 1, 0, let me just add this back over here. 0, 1, 2, 3, and 8, 6. This is LD. This is LD. That's basically the conclusion that we came up with. And now I'm going to ask you whether this set is Li or LD. Now, we can label these again. So the first vector is V1, and then V2, and then V3, and then V4, and then this one could be V5. And what I want to ask you is, do you see a way of writing one of those vectors in terms of the others? Some or all of the others. It's what the definition says.
No, it's LI.
Think it's LI?
I think, yeah. 'Cause I don't think you can make one like the other.
Brian?
You can do four minus V5 or
You're all around it. These vectors are LD, guys, actually. They are LD. It's not maybe obvious, but I'm gonna show you why it's pretty obvious. If you take V5, I can write V5 in terms of the others. Because V5 is what? X plus X cubed? Well, I can make the X by doing V2 minus V1. Right? And then I can make the X cubed by doing V4 minus V3. So this is just X and this is X cubed. Yeah. So this is your linear relationship. Let me do the same thing I did on the example over there. Let me put everything on one side of the equation. So I'm going to subtract everything to the left, and it'll be V1 minus V2 plus V3 minus V4 plus V5 equals 0. And this is my linear dependency. So that is what's called a linear dependency right there. Okay. And guys, linear dependence is a bad thing. It means we spent too much money on these vectors. We just spent $5,000 right here, but actually the fifth vector, we didn't need to purchase it because we can make the fifth vector for ourselves by using the first four vectors. And in so doing, we would have only spent $4,000. It would have been cheaper. So we spent too much money here as well. Now, I know what the question is you're going to have for me, which is, what if I didn't happen to notice? Like, what if I couldn't see this, like just glancing at it? Right? Brian had his finger on it. If I'd given him another minute, I think he would have figured the equation out. But you might be out there wondering, are we supposed to just sort of see this in our head? Or is it possible to have a process that would tell us for sure whether our vectors are Li or LD? Because I don't know if this was a messier example, I don't know if I could see how to write one of them in terms of the others. It's kind of a guessing. You're just kind of guessing at it. So the question is there a foolproof way of always deciding whether your vectors are Li or LD? And there is, as a matter of fact. I'm going to, in order to explain what it is, I need to rephrase what Li and LD means. So I'm going to rephrase it here, guys, really quickly. Namely, the set V1, V2, ... up to Vn is LD if and only if. So I'm going to give you another way of thinking about what LD means. I mean, I put the definition here. At least one of the vectors can be expressed in terms of some or all of the others. But how could I rephrase that? Here's the way we can rephrase that. This is if and only if there exists constants, and these are going to be C1, C2, and ... up to Cn. Sorry. C1, C2 up to Cn. And now for the three most important words that I'm going to write down on this side, which is not all zero. Not all zero, such that in spite of that, C1 times V1 plus C2 times V2 and dot, 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 up to Cn times Vn is equal to 0. This is what LD really means when we rephrase it. And, you know, you can go back to our examples and you can understand, like what I've written right here, guys, at the bottom of this board. What I've put into this linear combination here is literally what these two blue boxes are illustrating in these two examples that we've looked at. Right, so on this example that we just did a moment ago, the C1 is 1, the C2 is -1, the C3 is 1, the C4 is -1, and the C5 is 1, right? Those are the constants in front of the vectors in this linear combination. So you have your C1, C2, C3, C4, and C5. Yeah. And they're not all 0. Same thing over here on this linear dependency. C1 is equal to 8. C2 is equal to 6. It is true that C3 is equal to 0, but these constants are not all 0. In fact, 3 out of 4 of them are not. So these vectors are LD if and only if there is a linear dependency where the constants are not all 0. In other words, what I'm saying here, guys, is that I can cancel my vectors out to 0 with an interesting linear combination. I mean, I could have canceled them all out by just putting zeros in front of everything. 0 times V1, 0 times V2, 0 times V3. I could have done that. Well, that's cheat. That's cheating, basically. I'm saying that for the vectors to be LD, there has to be an interesting way to make them cancel out. This is what I mean by an interesting way. And this is what I mean by an interesting way. They're canceling out without just putting zeros in front of all of them, if that makes any sense. Yeah, so that's rephrasing LD. I also want to rephrase LI. Okay, so I want to get a little bit of a rewrite on that as well. And then once we have these rephrasings, I'll be able to show you a really easy way to do the LI-LD test. Okay, we already have a spanning set test. Now we're going to have an LI-LD test. So here is the rephrase that goes with LI. Here is the rephrase that goes with LI. Namely, the set V1, comma, V2, comma, dot, 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 up to Vn is Li. It's Li if and only if, and guys, it should be the opposite of this one. Because remember, Li and LD are opposites. They're opposites. So what's the opposite of there exist constants not all 0 such that this is true? The opposite of that would be that there do not exist constants that are not all 0. In other words, the only way to get your vectors to cancel out, so this would be C1 times V1 plus C2 times V2 and dot, dot, dot up to Cn times Vn. The only way to get your vectors to cancel out in a linear combination is when all of the constants are equal to 0. All of the constants, they have to be 0. In other words, the only way to get your vectors to cancel out in a linear combination is by cheating, by putting zeros in front of every single vector. Of course, that'll get everything to cancel out, right? But that's kind of a cheating way to do it. So if you have to cheat to get your vectors to cancel out, then those vectors were Li to begin with. But if you can find interesting ways, which is what these two blue boxes are showing in the examples we've done, if you can find interesting ways to get your vectors to cancel out, well, that's LD. And those are linear dependencies. Those are linear dependencies, exactly. So what we actually can do, and let's just do an example. Actually, I think I'm gonna take this example right here. So let me keep it on the board. I'm gonna come erase this side. Let's ask whether those three 2x2 matrices are Li or LD.
If you were to throw in the vectors into a matrix and you add them up, wouldn't that prove to you that it's linear dependent?
We are gonna throw these vectors into a matrix right now. Yeah. That's exactly where we're going with this. Yeah, so let's try this example, guys. Everybody with me so far? This is kind of I have to be honest with you, linear independence is kind of a slippery concept. Sometimes it takes a little getting used to. So I just want to be as clear as I can. But let's just take the exact same matrices that we used on that warm-up problem. 1, 2, 2, 2, comma, and then 1, 3, 0, 1, and then comma 0, 1, 1, 0. And I would like to ask, is that set Li or LD? Now, the way we were talking about this 5 minutes ago is, well, we'll stare at this. Can we write one of those matrices in terms of the other two? If we can, that's bad. If we can't, that's good, right? It's either good or bad, guys, right? So, but when we did this example, we had to kind of just get lucky. Oh, I happened to notice that the last vector is the second one minus the first one plus the fourth one minus the third one. We had to get lucky. So do we have to get lucky here also? Do I have to figure out, can I write this one somehow using these two? Well, you know what I'm going to do? I'm going to try it. I'm going to solve this one, guys. I'm going to try it. By the way, let me point out, we are already not very happy with these vectors because the answer was no. They were not even a spanning set. So we have spent $3,000 here, and we did not even come up with a spanning set for M2 of R. Now I'm trying to figure out, did I spend too much money in even trying to get my spanning set? So let's just try this. Let's set up C1 times the first vector plus C2 times the second vector plus C3 times the third vector. And we're going to set that equal to the 0 vector. In other words, I'm just playing with this equation here, right? Which is, of course, the same as the one in the box here. I'm just asking, if I try to set up this linear combination, the question here now, the question with what I wrote in blue is, do the constants have to be 0? Or could I solve them without the constants being 0? Is there an interesting way to cancel these vectors out or not? That's the question. It's different than the question we asked in the last section. In the last section, I would have been putting number symbols here. And I would have been asking, can I solve it at all for those constants? Consistent or not consistent? That was the question basically in the spanning set question. But now I'm asking a new question. I'm asking, are these vectors Li or LD? And for that question, this is what we need to do. This time, guys, there's no question. There's no question at all whether you can solve for these constants. Of course you can, because I can choose 0 here, 0 here, and 0 here, and it will work, right? But that's not the issue now. The question is, can we solve this system in an interesting way, other than just throwing zeros in front of those terms? Can we find some other way to do it? Well, what I'm going to do is I'm going to take this equation and I'm going to make 4 equations out of it. I'm going to go upper left corner of the entire equation. If I read across the upper left corner, I have C1 times 1, and then plus C2 times 1, and this is equal to 0. And then if I do the upper right corner, by the way, guys, in a few minutes, you'll realize we will never have to do all of this work. I'm playing silly with you for a minute because I don't like to just say, oh, just do this. I like you to understand where it's coming from. The upper right corner has a 2C1 plus a 3C2 plus a C3. That adds up to 0. The lower left corner, I've got a 2C1 on the lower left, and then a plus a C3. That's equal to 0. And then on the lower right corner, I've got my 2C1 plus C2 equal to 0. So I make that little system. Real quick, what am I going to do with this system? Throw it in a matrix, right? I'm going to definitely throw that into a matrix. So the first equation is C1 plus C2, no C3, adding up to 0. The second equation is 2C1 plus 3C2 plus C3, adding up to 0. The third equation is 2C1 plus nothing plus 1C3, adding up to 0. And the last one is 2C1 plus C2 plus nothing, adding up to 0. It ends up in this matrix. And my question for you is, have you seen that matrix anywhere else today?
Was that the first one we did?
I've been so careful to not erase this middle board because I knew I was going to want to make the comparison here. This was the example we did. We took these three matrices, right? And what happened? We laid the matrices into the columns of this bigger matrix, right, in blue. But what were we doing over here? What we were doing over here was putting number symbols in the far right column. What's the only difference now? With this LILD question, the only thing that changes, right? The first column's the same, the second column's the same, the third column's the same. The only thing that changes is all zeros in the far right column. And so you know all those EROs that we did over here? We don't really need to do them again because it's going to be the same end result. The only thing different, I'm just going to say ... from above, or I'll just say C above. The only thing different is the far right column will be 0, specifically 0. This far right column is all zeros, and it will stay all zeros. Oh, sorry. I'm supposed to get the row echelon form here. It will stay all zeros all the way through the whole thing. So 0, 0, 3, 0, and then 0, 0, 0, 0. So this is exactly this matrix right here, except with a column of zeros on the far right. I'll circle my pivots again because it's always a good idea. Remember that your unknowns here, your unknowns at this moment are the C1, the C2, and the C3. The question is, do the constants have to be 0, or is it possible to have non-zero solutions? So can you tell me, is there going to be any solutions for these constants other than 0? Do I have any free variables? Every column has a pivot, right? There's no free variables there. In fact, if you back substitute, right, the bottom equation tells you that 3 times C3 is 0. Well, that means that C3 is 0, has to be 0. And then plugging that into the previous equation, C2 plus C3 has to be 0, but C3 is already 0, so C2 has to be 0. And then back substituting from there, we also derive that C1 has to be 0. The only way that we could make that linear combination cancel out to 0 was with all of those constants being 0. Guys, that means that these vectors are Li. That's a good thing. This is actually what you wanted to have happen. So they were not a spanning set. That was kind of a bummer. but at least we didn't spend too much money, right? We spent $3,000 here. We could not have gotten away any less than that. Caesar.
Is there a correlation between no spanning sets and LI?
That is a great question. Is there a correlation between these concepts? Because I seem to be kind of getting excited about that. It turns out that they can be uncorrelated, that you can have any possible scenario. And I would like to show you another fresh example now where, you know what we're going to do on this next example? We're going to solve both the spanning question and the LI question in a single problem. So I'm going to put them together, right? This section, guys, goes with the last one. So we learned about spanning sets. The only difference was with spanning sets, we had these number symbols over here. And now we're saying, oh, for the LI question, I just need to put zeros there. That's really what it comes down to. Let's try another example. Let's take a fresh example here. And then I think we'll take a little break after we kind of tie this together. Oh, I love this stuff. Can you tell? I really do. I've spent my career doing linear algebra, so I better enjoy it. Yeah, so let's do another example. Another example here, guys, is the set of. So I'm going to use the matrices again. Let's take 1, 0, 1, 2, comma, -1, 1, 2, 1, comma, 2, 1, 5, 7. But this time, I'm going to ask a 4-part question. I'm going to ask, is this a spanning set? Not a 4-part question, just a 4 answers question. A spanning set for M2 of R. Is it Li? Is it both? Or is it neither? This is the question I want to ask. So, do those 3 matrices, do they form a spanning set for M2 of R? Are they linearly independent or not? Or are they both? Or are they neither? That's the question. Well, let's go straight to the matrix this time. Okay, so all of this work here, guys, that we just did on that last example, and I talked about this in my video as well, and last week as well. We don't need to write all of it down, right? We can go straight from these 3 matrices straight to the columns being filled in here. Right? The first matrix is right there. The second matrix is right there. The third matrix is right there. Let's do the same thing here. Let's put those 3 matrices directly into these columns right here. Watch how this goes. So the first column is 1, 0, 1, 2. The second column is -1, 1, 2, 1. And the third column is 2, 1, 5, 7. So I'm just going from upper left to upper right to lower left to lower right. As long as I do each matrix the same way, this is totally okay. All right? And I'm going to augment this matrix. Now here's the interesting part. If I was asking the spanning question, I would put number symbols here. But if I was asking the LI question, I would be putting zeros there. So you know what I'm going to do? I'm going to put them both there. I'm going to multitask, and I'm going to answer both the spanning question and the LI question at the same time by simply doing kind of a 0/ number symbol. So what goes in the far right column is either a column of zeros or it's a column of number symbols, as we learned on Thursday last week. And either way, that far right column never changes. It never changes. My constants here, guys, are C1, C2, and C3. Those are the unknowns. And let's just do our EROs. I've already got a nice pivot in the first 2 rows. But I need to get some zeros below these pivots, so I'm gonna do a couple of EROs. The first row can be left the same. I'm doing the zeros and the number symbols simultaneously. We're killing two birds with one stone is the saying, I think. Yeah. Second row stays the same. And now I've got to do A13 of -1. So that's going to be 0, 3, 3, and then 0/number symbol. And then I'm going to do A14 of -2, which creates 0, 3, 3, and 0/number symbol. Like I'm literally turning off my brain in the far right column. Yeah, you just recopy the same thing every time. By the way, I don't know if you guys have noticed, I'm getting a little bit more chill about the ERO writing. I'm not writing down AIJ of whatever and all that stuff here. We can kind of get away from that a little bit now because we've been doing it for a month. I feel pretty good about it. You can see now that the second row is just going to wipe out the third and fourth rows. So, you know, we can just quickly go straight to that conclusion. We don't need to like do a whole lot of effort for that. So 0, 0, 0. Excuse me. Yeah, so your third and fourth rows just pretty much get wiped out. So let's talk about what the conclusion is from this matrix. And again, it is still really, really good idea to circle your pivots. That's the one thing I'll say. You'll be seeing me do that the entire semester, circling those pivots, okay? So my first question is, when I have number symbols that I'm looking at, does a pivot go into the far right column? Be careful. So I got this pivot here, this pivot here. Let's go to row 3. 0, 0, 0. If this was a number symbol, wouldn't that be circled? And that's bad, right? Pivot in the far right column means it's not consistent. That actually tells you that this is not a spanning set. Having that pivot in the far right column tells you that this is not a spanning set, which of course means it's also not both. It's not going to be both. It's not a spanning set because that pivot is going into the far right column, right, Oscar?
And then I've noticed that we have a free variable. Does that play into being linear independence?
I should just hand you, I should go take the day off. I'll bring you up for the marker because you're explaining exactly what I was going to say, which is that when I ask the LI question, C3 is unpivoted, which means it is free. It is free. And having a free variable, I'll just call it T, having that free variable there, guys, is bad, right? It's basically a bad thing. If you think about that, we can now back substitute. I'm actually going to do this. So if C3 is equal to T, and I look back on the second row here, you see on the second row, C2 plus C3 would be 0. So that means that C2 is actually negative T, because these two have to add up to 0. And then if I want to know what C1 is, so C1 minus C2 plus 2C3, if we set that equal to 0, I can solve for C1 now. C1 would be C2 minus 2 times C3 is actually negative 3T. The point is there is a free variable here. And in this case, guys, in this case, free variable is a bad thing. Because what it means is that it is not the only way to get your vectors to cancel out is by putting zeros here. In fact, there are other ways to get your vectors to cancel out. So these vectors, my friends, are not Li either. This is actually the worst possible answer because it means you spent too much money to begin with, and you did not even get a spanning set out of it, right? You didn't get what you bargained for, and you spent too much money anyway. So it's like a lose-lose scenario. It's the worst answer you could have. Actually, we could write down the linear dependency too. And you will be asked to do this on the homework for Friday. If you have the free variable here, you can actually choose a number for t. And does anybody have an idea what number I might want to choose for t? I'll give you a hint. There's only one number that you should not use. But you could tell me almost any number for t that you like. But if I want to create my linear dependency, I have to avoid one value of t. Anybody know what it is? We should avoid 0. Because guys, if you choose t to be 0, you actually would be making all of your constants 0, which is not what you're trying to show right now, right? So I usually choose t equals to 1, but you don't have to do that. If you choose t equal to 1, then c1 is -3, c2 is -1, and c3 is 1. And if we want, we could actually write down our linear dependency. -3 times the first vector, which is the first matrix, and then minus the second matrix, and then plus the third matrix is equal to all zeros. This would be your linear dependency. That would be your linear dependency right there. How long would it have taken us to find this if we were just grasping at it? If I just gave you these 3 matrices and I said, are they Li or Ld, right? Would you have come up with this right away? I don't think I would have. I probably would have given up after a minute and said, oh, I bet they're Li. And then I'd find out later, no, they actually are Ld, right? And so I hope that I've given you a little reassurance now that if you're asked whether your vectors are Li or Ld, this is a foolproof process that will ultimately either end with free variables or without free variables. This one was without free variables. This one did have free variables. And if you have free variables, then you can create your linear dependency by just choosing, in this case, I chose t equal to 1. Yeah. Question C.
So for every one of these problems, essentially, so if it was linear dependent, we have to, that would be like our explanation basically on why it's linear dependent.
You could tell me that it's linearly dependent by just pointing out that we have free variables here. So you wouldn't need to give the linear dependency itself unless they ask you for that. Some of the homework problems will ask you to write down a linear dependency. But here, yeah, we could have just stopped right now. The minute that I see that there's a free variable, it's game over. It is LD. So what I hope you guys are appreciating is that the spanning set question and the LI question, they are set up the same way. The issue is how you are interpreting the row echelon form that you eventually get. For the spanning question, you're just asking, does the pivots go into the far right column? Here it did, which was bad. For the LI question, you're just asking, are there any free variables or not? Here there were, and that's also bad. Right? You with me? I actually have a question for you. If I take these 3 matrices, and I give you 6 hours to change all the numbers in these matrices as many times as you want, and I ask you whether they're going to be a spanning set for M2 of R, do you think you could choose a better numbers to put into these matrices that it would then be a spanning set? Do you think that would be possible? Obviously, these were not a good choice. This turned out very bad. They're not a spanning set. Do you think we could have had a spanning set if we had better numbers in those matrices? Of course, if I have better numbers in these matrices, it just means I'm changing the first 3 columns. Right? I'm changing the first 3 columns. In a best case scenario, I could maybe get a third pivot here. Right? But look how many rows you have. Right? Would you agree that if I'm gonna have these three pivots like this, I have to have zero below these pivots, well, back here, and here you see it. Below the pivots, you have all zeros, right? At best, your pivot is gonna go way over to here. And it'll be in the far right column of the bottom row rather than the third row. What I'm trying to say, guys, is that there would have been no choice of three matrices that could have spanned M2 of R. You must spend at least $4,000 to span M2 of R. If you try to only use three, even if you change these numbers and try to get clever with what numbers you pick there, because this matrix is tall and skinny, right? You see that? It's got 4 rows and 3 columns. Because of the shape of this matrix, even if your pivots work out great, here, even so, you get this bad row down here with 0, 0, and 0, which forces that pivot into the far right column. We're going to say much, much more about this later. The idea that if I'm working in M2 of R, and if somebody only gives me 3 vectors, I can say immediately, without even taking a breath, that they will not be a spanning set. The shape of this matrix is just not going to work for that. Yeah. So that's kind of a nice preview of what I'm going to say in just a little while. All right. Let's take a 10-minute break. I'm going to let you guys kind of chew on all of this for a few minutes, and then we'll come back and I'm going to try to put these concepts together just a little bit. Yeah.
I was gonna ask, with those matrices, with those, could you make them into an expression so that you can try to find it instead of having to do all this?
I mean, you can just take these matrices and see this at a glance. That's more power to you. That's fine. But I don't think it's obvious. I think this is kind of your systematic approach to deciding whether your vectors are Li.
It's because earlier we had a vector set where it was like 1 comma and then like t plus 2 and then like multiple expressions. With that, you can put that in the matrix, right?
We're gonna have to talk about this later. Yeah, I'm not following.
Let me see.
I am not following what you're saying.
Like this, basically. I could be wrong again. So like with this, could you not put this in a matrix? And
Yeah, you would put that into a matrix. So the vector 1 would go in like this.
and by doing that, what I'm saying is that like if we had something like this, could you not put this in that form? And just from there, just like tell you whether it's Li or Le.
Changing that into
wouldn't
polynomials,
help.
you mean?
Yeah, yeah.
No,
It wouldn't help.
no.
Okay.
Well, it does not only does it not help, it doesn't make any sense.
Okay.
No, it's a totally different universe. I mean, if I wanted to put them into a matrix, these are what the polynomials were. 1 and then 1 plus x,
Yeah.
1 plus x squared, 1 plus x squared plus x cubed. Then we had x plus x cubed.
Okay.
Now on this one, and we could ask the same question, is it a spanning set for, I guess it was P3 of R, and is it Li or LD? On this one, you see that there is a free variable right away. And this matrix, so I was just talking about how this matrix is tall and skinny. This one is sort of wide and stretched out. And because of that, it has more columns than rows. Because of that, this 5th column must have a free variable. Because you can't have more than 4 pivots if there's only 4 rows in the matrix. But you have 5 columns, which means you are for sure guaranteed to have an unpivoted column.
So if it was
Which means free variable.
So if it was a square matrix, then for sure.
Square matrix is a different story. Different story. I have to talk slowly about these ideas. If it's a square matrix, then it's a different outcome. But basically what I'm trying to say is that if the matrix is tall and skinny, then no matter what the vectors were that you started with to make that matrix, they cannot span V.
Okay,
But if your matrix is wide and stretched out, then those vectors cannot be Li.
okay.
Do you agree with that? If I take these polynomials. Let's say I give you 6 hours to change the coefficients of these polynomials. And I say, Raphael, you've got 6 hours to change the coefficients of these polynomials so that they become Li. We've already said that as it stands, these are LV. So the question would be, could you change these numbers to make them Li? And the answer is
No.
you would simply be changing what's the numbers here, but the shape of this matrix
Yeah.
would still be like this. The real problem here is that you have spent $5,000, which is too much in this context. So in that analogy I was
Okay,
giving earlier.
okay, thank you.
Okay.
You had like a square matrix. I'm trying to see how determined to play here, but. if we had
It is
another-
going to come into it.
Okay.
Yeah, I'm gonna talk about it after the break. If you had a fourth matrix, then this would have been 4 by 4. And then it turns out in that case that those 4 vectors would either be both or neither. It couldn't be one without the other. So these are the 2 things you'd like to have. The best answer on the board here is both. You'd love to be both, because if it's both, that means you do have a spanning set and it was cheap. Like you got the cheapest possible spanning set. And you're circling both, that's what you have. So in the case of a square matrix, that is possible. What I'm trying to show here is that if the matrix is tall and skinny, you'll never get that. If the matrix is wide and stretched out, you'll never get that. So if you want to even have a chance of having the best answer to the question, you must have exactly the right shape of a matrix, which is a square size matrix. And then determinants are going to come into that.
I was just gonna mention, today, you leave like 2 minutes early.
No sweat, no sweat, yeah. Anthony, could you do me a quick favor? Would you mind erasing the board for me? I really appreciate that. I gotta run to the restroom. I'll be right back. Thank you so much. Give you a chance to stretch out a little bit.
Um,
Now, for those of you who like nice summaries of what we've done, and if you have a cell phone, want to take a picture of it, this would be a highly recommended synopsis. It basically in one uh, iPhone photo, you are summarizing the last hour of the lecture, right? If I give you a set of vectors, the two questions that we care about the most are they a spanning set for V? And are they Li? And to answer both of those questions, we sort of set things up the same. We just lay our vectors into the columns of a matrix. The only difference is that for the spanning question, I need to put number symbols here. But for the Li question, I need to put zeros in this far right column. And then how you interpret the result, which really just comes down to where the pivots are, is really what determines a yes or a no on each of those two questions. So this is a sort of a back of your hand summary of everything from those two sections. Yes.
just really quickly, for the Li, if you have a free variable, would you go directly into the dependence?
If they ask you to write down a linear dependency, you could then use the free variable to do that. We showed how that works on that earlier example. But if they just want to know, are the vectors Li or Ld, you would only have to go far enough to decide whether there was a free variable or not, because that's enough to answer the question. Yeah, exactly. A few people were talking to me during the break about how sometimes even just the shape of this matrix will dictate that something here is impossible. Like if it's a tall, skinny matrix, then there's no way it could be consistent. If it's a wide, stretched out matrix, then there's no way that it could avoid free variables. So it turns out that if you want to get a yes on both categories, which is really ultimately what you want to have a spanning set, you want it to be as cheap as possible. If you are going to get a yes on both categories, you actually have to have a matrix that's like a square size. Okay, I'm going to write that down shortly. Before I do that, though, I have one final remark about linear independence that I'd like to make right now, and then we'll explain. We'll kind of spend the last few minutes putting it all together. By the way, a couple people had questions over here on the sideboard. I put hints there. So if you want to take pictures of those hints, I think that should be good enough to get you through on those problems. I won't spend any extra time talking about them now. So here is the remark. In the case of two, oh, this is so important. In the case of two vectors, we can make a very easy determination about whether they are Li. Just basically glancing at them. In the case of two vectors, the set V1, V2 is Li if and only if they are not scalar multiples of each other. Right. If and only if they are not scalar multiples of each other. It's really nice because usually you can just look at your vectors and tell whether they're scalar multiples of each other. The problem with this remark, guys, the problem with it is that it only works if you have two vectors. You might have noticed most of the examples today, I had either 3 or 4 or 5 vectors flying around. This is only for 2 vectors. So just let me give you an example that would have 2 vectors. So if I had, let's say, the set of, let's just do x squared plus 2x plus 3. And then let's suppose we took another one, which was 5x squared plus 10x plus 15. So these are quadratic polynomials, and you might just glance at it and notice that the second one is a scalar multiple of the first one. And because they are scalar multiples, then this set of vectors is automatically LD without even taking a breath, right? Basically, in this case, if I label, kind of notice I like to label these vectors. This is V1 and V2. In this case, on an example like this, all that we were saying here, guys, is that V2 is just 5 times V1. And this would be linearly dependent, right? If I can write one of my vectors in terms of the other, then they're LD. So, of course, this is bad, right? This is bad. We're spending $2,000 right here. But the second vector, we should have just been able to build it out of the first one. So it should have been possible to get away a lot cheaper. Just to really drive my point home about the 2 vectors, I just want to give you one more example where I give you more than 2 vectors. Suppose that I gave you 1, 0, 0, 1, and 1, 1. Now this is 3 vectors. And if I look at the 3 vectors here, I could actually draw them, right? The first vector is 1, 0 here. And then we have 0, 1 here. And then 1, 1, we could graph that one like that. And what you can see just visually is that no 2 of them are scalar multiples, right? So V1 is here, V2 is here, V3 is here. There's no scalar multiples. They are not scalar multiples of each other. However, these vectors are LD. And you can clearly see it. V3 is just V1 plus V2. Right, so it's these vectors, so this set is LD. What I'm trying to show with this second example is that the remark is not valid if I have more than 2 vectors. If I have more than 2 vectors, I can have none of them being scalar multiples of each other, and yet they're still LD. So be careful. Be careful not to read too much into this remark. That's usually the problem people have is they get too hung up on this scalar multiples. And it only works for 2 vectors. Whenever we have more than 2 vectors, not gonna happen. Okay. So far, so good?
So for sure, it's gonna be linear dependent if you have 3 vectors and one of them is the sum of the third one, right?
Yep, if I have a linear dependency like this, that's LD. It's LD. Okay, guys, I want to talk about this most favorable outcome, which is a spanning set that is as cheap as possible. And I'm going to talk about this kind of at the start of this next section here. This is the cornerstone concept of vector spaces. It's something called basis and dimension. Somebody mentioned the word basis earlier, and we are now going to look at it. basis and dimension. So let me give you the definition of a basis, first of all. A basis for a vector space is a set of vectors S. A basis is a set of vectors S such that two things are true. First of all, S is a spanning set for V. So it is a spanning set. It does span V. And secondly, S is Li. S is Li. Right. So a basis is a yes on spanning set and a yes on Li. That is a basis. It's the best possible outcome. You spanned your vector space and you did it as cheap as you could have gotten away with, right? That's like the ideal outcome. Let's write down an example. Let's write down an example. Suppose that V is R3. So start with one that's kind of easy to think about. R3 is a nice vector space. And let's take S to be the set of 1, 1, 1, and then 2, 0, 6, and then 4, 2, 2. And I'm going to ask, is S a basis? Back over here to get that written correctly. Is S a basis for R3? Is it a basis for R3? Guys, when I say basis, that's really just, you know, we're really not doing, okay, so here's my point. In this section, we're not really doing anything new. We're just putting together the two previous sections. If I say something is a basis, that's just meaning it's yes on spanning set and yes on Li. Okay, so we already know how to do this because it's just putting together the stuff we learned previously. The way we would do this is lay the vectors into the columns of this matrix. So 1, 1, 1, and then the second column is 2, 0, 6, and then the third column is 4, 2, 2. And I'm going to multitask and augment this with either zeros or number symbols. I'm not going to do them independently. I'm going to just do them together. And I would like to just have you guys take my word for the EROs because I want to kind of get to the punchline here. So we'll skip showing all of our work on the EROs, but I will give you the row echelon form here. First row stays the same. The second row is going to become, if I carry out my EROs, it should become 0, 1, -1 on that row. And then on the third row, 0, 0, and 1. It's going to look like that. Taking a look at that, guys, is this consistent? Yes. Are there any free variables? No. So we have no free variables, so it is Li. It is consistent, which means it is a spanning set, so we win, right? This is the best outcome. Because of this, this implies S is both a spanning set and it is also Li. And so the answer here is yes. This is a basis. This is going to be a basis, which is pretty cool. Now, this is the first time today that we have an example where the matrix that we created, at least on the left side of the bar, the matrix that we created was actually a square size matrix. As you can see, this is 3 by 3. The earlier examples, we had a 4 by 3, we had a tall, skinny matrix. We've also seen wide, fat matrices, right? But this is the first time when it's a square matrix. And when you have a square matrix, you have another tool in your toolbox that you can use. Does anybody remember what it is? The determinant, yes. Guys, you can tell that the determinant of this matrix is not going to be 0. Why is that? Well, it's because I know that this is actually invertible. This matrix has full rank. Going back to the chapter 2 again, right? This matrix has full rank. Every row and column has a pivot. So this is an invertible matrix, so its determinant would be not 0. And oh, how about that? If the matrix is invertible, which I always have thought of as being a good thing, I can now tell you one more good thing, which is that when you set up this matrix, and if it's invertible, it's going to mean that yes, we have found this cheapest possible spanning set for V. It's our basis, right? That's actually ties together all really nicely. Let me write down that as another remark. I think I can just put another remark here. This is an easy section in some ways, guys, because we're just putting together the 2 previous sections, right? So let's just add that as a remark. Another remark here is that in the case where A is a square matrix, which is what we just saw on that example that we just did. In this case, then S, and sorry, so A is just this matrix with V1 and V2 up to Vn. And I'm ignoring the far right column for now. If I lay those vectors down into A, then this set V1, comma, V2, comma, dot, 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 comma, Vn is a basis for V if and only if the determinant of A is not 0. Is not 0. That's a good thing. In other words, A is invertible. This is what we have there. By the way, if the matrix does have a determinant of 0, in other words, if you do your EROs and you, okay, don't change your notes. I just want you to listen for a second. If this had come out like that, so that the matrix is not invertible, then actually it would no longer be a spanning set, and it would also no longer avoid free variables. You would actually go directly from both to neither. Remember the 4 choices? Is it a spanning set? Is it Li? Is it both? Or is it neither? When you have a square setup of the problem, it's either going to be both or neither, depending on this determinant. Right? So this is the both case right here. It is a spanning set and it is Li. Isn't that cool? Okay. Well, I'm going to write all of that down as well into a nice little summary, kind of like the summary that I'm erasing right now in just a few minutes. But I might end up having to wait until Thursday for it because I want to make hopefully one last kind of observation for today, which is that do you think there's only going to be one possible basis for a vector space? Be true that any 3 by 3 matrix here, as long as it was invertible, by the time I do my EROs, I have pivots going So this was originally with a pivot here. I can think of thousands of 3x3 matrices that are invertible. And every single one of them is going to correspond to 3 vectors that were put into those columns that turned out to be a basis. So guys, a basis is not unique. And I want to have that in the notes. A basis for a vector space is not unique. There isn't just one. So as an example, if we go back to R3 again, because that's the one we just worked on a minute ago, we go back to R3 again, there's a much easier basis for R3 than this one. There's a much easier basis. The easiest one I could think of, actually, does everybody think they know what it might be? The easiest basis for R3? Or like maybe just the most obvious natural one? It's called the standard basis. What vectors do you think those would be? If you're Calc 3 professor, whoever you took 250A from, you spent a lot of time working in R3. Were there any vectors in R3 when you're looking at your XYZ R3 space? Were there vectors there that were kind of like, these are the building blocks. These are the ones that make the whole space. Yes, Arnav?
I, J, K.
I, J, and K from your Calc 3 setup. And those are, it's exactly right. Those are the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. That is also a basis. And this is actually called the standard basis for R3. That is the standard basis for R3. Is there any doubt that that's a basis? I mean, gosh, if you put these vectors into a matrix, there's your matrix. I mean, that has a non-zero determinant, just obviously. But you can see that there'll be lots of other bases here. Caesar?
So maybe I'm not seeing the big picture. You're saying this is the best possible outcome, right? Cheapest and this and so.
Correct.
Why? I don't get, like, for me, it's like, oh, if it's not any, it works also easy. But if it's if it works also easy, it's kind of like, what's the point of it being the best? I'm just confused.
It's a good question. No, it's a really good question. So we would like to have so the first thing is you have to be motivated that you want to have a spanning set for your vector space. Because if you have a spanning set, such as these 3 vectors in R3, then every vector in that vector space can be written in terms of these. So that's the power of having a spanning set. But I want to have a cheap spanning set as well, because if instead of these 3 vectors, if I toss them out, and instead I hand you 25 other vectors that cost $25,000 and said, here you go. Well, they might be a spanning set, but now you don't have a nice way of like figuring out, well, how do I put these 25 vectors together to write X, Y, Z in terms of those vectors? Your linear combinations would become long. They would not be unique. It would be messy, messy, messy compared to something as clean as this. So you're trying to have a spanning set, but you want to make it as efficient, I guess that's the word, as efficient as possible in spanning the space. It's a great question. I'm out of time. The thing I want you to think about between now and Thursday, I just said that a basis for a vector space is not unique. But is there something that every correct basis would have in common? That they would all have to have in common. Say for R3, right? Is there something about this basis that's the same as this basis? And I'm talking about something that doesn't require any math background. Just saying, just looking at them. Is there something, if you looked at these vectors compared to these vectors, there's something that's the same about them? I was going to give you 2 days to think about it, but we don't need 2 days. What is it?
The number of them?
The number of vectors, the number of vectors. Guys, if I add a fourth vector, I'm gonna add a free variable. Or if I take away a vector, I'm gonna have a pivot going over onto that number symbol. Either way, if I give you too many vectors or not enough vectors, everything crashes down. So I'll write all of that into the notes on Thursday. That's called the dimension of the vector space. It's how many vectors are actually in a basis for V. Thank you so much for your attention today. If you didn't get your midterm back, I do have some exams up here that I would love